So in this video, we're going to consider our second current process, which is diffusion current density. And so in this process, we're not applying an electric field. And in this case, we just have random particle movement, which is related to the temperature of our material. So let's take a look at a group of electrons. So here I've labeled group 1. So we have just sort of a bunch of electrons that sort of randomly drawn in here. And so what we're saying is that these electrons are moving randomly. So if we sort of look at specific ones, maybe this guy here is moving in this direction, maybe this one's moving here, this one's moving here, this one's moving here, this one's moving here. So they're all moving in sort of these random directions. But if we were to look at sort of the whole material, we would see that our net movement would be 0. So we would have 0 net current if we're just looking at this group 1, because basically for every electron moving this way, there's going to be equal movement from another electron moving this way, such that it cancels out. And so of course that's same for up, down, diagonal, certain ways. There's always going to be some opposite direction going on. And so that's just from kinetic theory. So let's say, however, that we have a second group of electrons. So let's move this over, and let's say somehow we were able to keep these two groups separated such that we have one group on the left, group 1, which is a large group, and over here on the right, we have a smaller group of just a few electrons. And so of course we have the same principle going on here in terms of if we're just looking at group 2, we're going to have maybe this guy's going here, this guy's going here, this guy's going here. And if we were to look at all of these accurately, we would see that ultimately we'd cancel out and we'd have no net movement. But let's sort of look at what happens if now the two groups are sort of allowed to interact with one another. So from kinetic theory, we know that we have random motion of these electrons. So from group 1, roughly half of the electrons are going to be moving towards the left. Roughly half of them are going to be moving towards the right. So let's use green for group 1, and because we have more, let's make our line a little larger here. So for group 1, we have roughly half of our electrons moving this way. So let's say that's roughly 1/2 of our electrons, and roughly 1/2 of our electrons moving this way. And so of course the same could be true if we're talking about moving up and to the left, down and to the right. Roughly half of the electrons are going in one direction, half are going in the other direction. Okay, so now let's switch colors to blue, and let's make our line a little smaller, and let's look at group 2. So the same basic idea is true for group 2. At any given time, about half of our electrons are going to be moving towards the left, and about half of our electrons are going to be moving towards the right. And so again, the same is true if we're talking about different directions, up, down, down and to the right, down and to the left, up and to the left, up and to the right. Half in one direction, half in the other. Again, it's just random motion, and it works out such that our net movement is 0 if we're just looking within one group. However, if we are considering these two groups have sort of been put side by side and can interact, we notice that we have a larger value here than we have here. So even though we have half of group 2 electrons moving from right to left, they're sort of overpowered by this half of the electrons moving from left to right from group 1. And so what we're going to end up having then is a net movement of electrons from left to right. So we have a net movement of electrons from left to right. And so of course, because our current direction is opposite of electron direction, what that means is that we would have a diffusion current moving in the opposite direction. So this would be our diffusion current going from right to left. So let's say this here indicates that we have a diffusion current moving from right to left. And so, of course, there are other examples of diffusion that you might be familiar with in everyday life. So, for instance, I had one professor who used to always love giving the example of somebody wearing a strong perfume or strong cologne. So, of course, if they walk in the room, you know, that cologne, those particles that smell of cologne are not going to stay right next to them. They're going to diffuse out into the room so that everybody can smell that as well. Of course, there are a lot of other simple examples to illustrate this purpose as well. So let's consider that same idea, but graphically. So if we look at this graphically, what we can do is we can plot our electron concentration, for instance, so N, over some distance. Let's just say it's x. And so this is just some distance in space. And so let's say we have some concentration curve that's linear and just looks like this. And so what that's saying is basically at some point here we have a lower electron concentration compared to some point further along in x. So we have some higher concentration. And so if we go back to the idea of our two groups, we see that the higher concentration area is going to cause a net movement towards the lower concentration area. So if we apply that same idea to our graph here, we see that here's our higher concentration, and there's going to be a diffusion towards our lower concentration. So this is going to be our electron diffusion in this case, from right to left. And as we said before as well, because our current is in the opposite direction of electron flow, we're going to have our diffusion current, for this case, going in the opposite direction from left to right. So this is our electron diffusion current density J. And so we could consider the same idea for holes as well. So let's do a similar plot. And let's say now we're looking at hole concentration P, and we're also looking at that across some distance. Let's say we have a similar plot that just looks like this, so some linear line. Again, up here would be higher concentrations, here is lower concentrations. And so what that means is, again, we're going to have diffusion from higher areas, higher concentration areas to lower concentrations. So we have hole diffusion from right to left. But because our holes are positively charged, that means that our current is in the same direction. So we have our hole diffusion current, or a hole diffusion current density, going from right to left in this case. So hole diffusion current density. And so using this graphical method, we can more easily write our equation for our diffusion current density. So our diffusion current for electrons, so let me write that out. So diffusion current for our electrons is given by J sub n is equal to Q times D sub n times D sub n, sorry, not D sub n, dn dx. So sort of let's define a couple of these things here. So our D sub n is our electron diffusion coefficient. And so that's going to be material dependent, and we're going to see in the next video how we can actually relate that back to our electron mobility. Our dn dx is, we can see from the plot, that would just be the slope of this line. To be more specific, we can just, or rather more general, we can just call this the gradient of our electron concentration. So gradient of electron concentration. Okay, so that is for our electrons, but if we want to characterize for our holes as well, because just like with our drift, our diffusion current is going to consist of electron and hole components. So for our diffusion current for holes, we're going to have J sub P is equal to, and I'm going to put a negative sign in here, so we're going to have negative Q dP times dP dx. And so the reason for that negative sign is because this current direction is now going in negative x direction. Our electron diffusion current, it was going in a positive x direction. So that's why we have the negative sign here. And similar definitions for our dP and our dP dx. So our dP is our hole diffusion coefficient, which is again just a material property, and we're going to see in the next video how that can be related to our hole mobility. And our dP dx, again, the slope of the line in that plot above, or more generally, the gradient of our hole concentration. And so as I mentioned briefly before, of course, our total diffusion current is going to be the sum of those two parts. So total diffusion current is going to be J is equal to J sub n plus J sub p, where in this case we're talking just about diffusion currents, not drift currents at the moment. So we can say, substituting in our equations, that's Q times D sub n dn dx minus Q d sub p times dP dx. And just like we saw with our drift current equations, it's not uncommon for one of these two terms to dominate over the other.